All right, let's talk about power functions. Now, what is a power function? A power function has a variable in the base, right? And it's raised to a constant power. So it involves an exponent, but don't get it confused with exponential functions, because in an exponential function, the variable is in the exponent. Here we have a constant exponent. We have a constant power of x. The variable is the base. All right. Now the standard form of a power function is just some constant, here we're calling it k, times x to the power p. All right. So it's just x to some power, but it could be multiplied by a coefficient, a constant. So in this first example, we're given some functions that may or may not be power functions, and we have to rewrite them to determine whether they are power functions or not. All right, so a lot of these are power functions in disguise, and it's really going to rely on your properties of exponents, right? You got to remember the properties of exponents in order to simplify these ugly functions, and so that you recognize that they are that they are power functions. All right, so if they're power functions, we're going to write them in the form k times x to the p power, and we're going to identify what k and p are. All right, let's take a look at this first one. We have negative 2x, and all of that is to the fifth power. So first thing I'm going to do, I have a power to a power, right? So I'm going to take negative 1 to the fifth power is going to be negative 1. So I'm going to put a negative out front, and then x squared to the fifth power is going to be x to the 10th. And then we have this 2x in the denominator. Now I have a common factor of x in the numerator, and then I have 10 factors of x in the denominator, so I'm going to cancel one of these x's and make this x to the 9th. And so what I have left is a minus, well, it's minus x to the 9th over 2. But that's the same as minus 1/2 times x to the 9th. I want to write it that way because I want to be able to identify my constant multiple, right? In this case, k is equal to a minus 1/2, and the power is 9. Okay? So that's what we're going to do on all of these. We're going to try to rewrite them in as a power function, but they're kind of ugly as they are now. So this one has a square root all around the stuff. Now remember, square root is a 1/2 power, and I can break this up into the square root of e to the 4th and the square root of the square, right? So square root of e to the 4th is e squared, and the square root of a square is just going to be the thing inside the square, right? So this is going to be 4x cubed, right? I'm just taking the square root of this whole thing. And now, okay, e's are always fun. I'm going to rewrite this as 4e squared x cubed. All right, because then I can see that, oh, this is my constant. Remember, e is just a constant. So 4e squared is something you could put in your calculator. It is a number. And then our variable x is raised to the 3rd power. So in this case, the constant is equal to 4e squared, right? And then the power is equal to 3. All right, let's look at this next one. Now, I can rewrite this using properties of exponents, right? Because I have a power to a power. So this is 8 times 3 to the 2x, right? I can multiply those powers. It's really, 3 to the x times 3 to the x, which is 3 to the 2x. But look at where the variable is. The variable is not the base. The variable is in the exponent. So this is an exponential. This is exponential. Exponential. It's not a power function. Not a power function. So there's nothing we can do to it to make it into a power function. It's just an exponential function. It's not the same as a power function. All right, let's look at this next one. We have 11 times the whole quantity, 2x minus 1 squared. Now, there's some things we can do to rewrite this. We could expand that square, right? And we get 4x squared, and then first times last times 2 gives us minus 4x, and then plus 1. And then we could distribute the 11, and we get 44x squared minus 44x, and then plus 44. But that doesn't help us. I can see there's some. This 44x squared is a powered function, but then we have minus 44x and plus 44. There's nothing we can do to rewrite that in the form kx to the p. So this is also not a power function, even though there are there's a sum and difference of power functions, but this itself is not a power function. Okay, so because we cannot write it in the standard form. All right, let's look at the next one. Now, again, we're going to use our properties of exponents. So I'm going to, first of all, I know that this is, I can pull out a 1/4, right? 1/4, and then I'm going to have x cubed, and this is x to the 1/2. I know that when I have a quotient of two power functions, I can, two powers of the same base, right? I can subtract the exponents, right? So I'm going to get 1/4 x to the 3 minus 1/2. 3 is 6/2 minus 1/2, so we're going to get 5/2. So the power of x is 5/2. So this is a power function. K is equal to 1/4, and p is equal to 5/2. All right, we got one more here. Now I'm just going to simplify this fifth power. So I'll leave this 4 as it is, and I'm going to bring the fifth power inside here. And -1 to the fifth power is just -1. And then this is the same as x to the 1/2, right? The square root is x to the 1/2. So 1/2 times 5 gives us x to the 5/2, right? And now that's in the denominator, so I can actually rewrite this. I'm going to bring the negative out front and call this a -4. Right? I can pull that out of the numerator, and then I can rewrite the 1 over x to the 5/2 as x to the minus 5/2. Okay, so this is a power function with a k equal to -4, and the p is equal to a -5/2. All right, that's it. Kind of tricky. Just remember your properties of exponents. All right, I'll see you in the next video for the next example.